All right. Thanks for the invitation and this great workshop. Today I'm going to talk about our group's recent work on offline multi-agent games. And thanks Miao for introducing offline multi-agent games, so I don't need to repeat many notations. So my talk is on offline reinforcement learning, and I assume you are familiar with it. I mean, it has many applications. Basically, we have a lot of offline data available and want to learn a good policy from this offline data. Okay. All right. So quick review on single-agent reinforcement learning in the offline setting. So here I'll focus on the I'll use this finite horizon episodic setting where, let's say, we have an agent interacting with an environment. At each time step, chooses an action, moves to the next stage, receives some reward, repeat for each times. And these are standard notations for value function. And our goal, let's say, here is to learn near optimal policy. Okay, epsilon here is the target policy. So V pi is the value function for policy pi, and V star is the optimal value function. All right. So in this talk, I'll mostly focus on the tabular setting. So we have finite number of states, finite number of actions, reward bounded from 0 to 1. And generally in this setting, the sample complexity depends on polynomially on SA, H, and 1 over epsilon. OK. And for offline single-agent reinforcement learning, basically we have a data set, say n tuples of this form. So for each I, it's one trajectory, and in each trajectory I have h time steps. Sampled from some, say, distribution which is induced by some behavior policy or data collection policy. Okay, and so rho here we denote as data collection behavior policy, and d rho h of some SA is state action distribution induced by rho and transition p. I think Zhou in the morning has already introduced those notations. So here in this talk, I'll mainly focus on one aspect, which is under what conditions on this data distribution that generates the data from this induced by this policy rho that we can learn a near optimal policy. Okay, so I'll talk about this is the main quantity I'll be talking about, and we'll see a difference in the single agent and multi-agent setting. Okay, so most of the results are just qualitative. There's no sequence of equations or inequalities, but mainly conceptual qualitative results. Okay, so what do we know about in the single agent setting? So this is a classical problem, and so one natural condition we put on this distribution is that, let's say, this distribution is quite diverse in the sense that it covers every state action pair. Okay, so I have some policy. It covers, which gives you a data set that covers every state action pair. So, like formally, you can say that there exists some constants, say C uniform, such that 1 over this distribution or that induced by the policy rho is upper bounded by C uniform, or inversely, like this, it has a lower bound density. Okay, for every state action pair. So because this is a distribution, so the C uniform always has lower bound, which is number of state and number of actions SA. Okay? So if you have such a condition, then it's very easy to obtain near optimal policy. Basically, you just estimate the transition and then reward, and then you do dynamic programming. You optimal the like best empirical policy based on your estimated transition and reward. And that policy actually guarantees you near optimal policy if you have enough number of samples. Okay? So this is a pretty classical result, and this is a tight bound here. All right. So a natural question is that whether we really need this assumption, because it actually imposes you need this data collection policy that cover every state action pair, but maybe we don't need it. Like we can cover only a subset of state action pairs. And that may be enough to recover the near optimal policy. And this comes to the single policy coverage assumption, which says that this behavior policy, data collection policy, only covers a single optimal policy. Right? So conceptually, you don't need to cover every stage in care in order to obtain a near optimal policy. As long as your data covers the optimal policy trajectory, then you should be able to kind of recover that policy. Okay? So that's the conceptual meaning of this assumption. And technically, this assumption states that there exists some constant that called C single, such that, let's say, there's some optimal policy pi star at every step h, this density ratio between the distribution induced by pi star over the density or this probability mass of this data collection policy distribution is upper bounded. So basically, for this optimal policy pi star for every stage transaction pair is always covered by this data collection policy rho. Okay? So under this assumption, you can imagine that in the best case, C single can be as small as 1, because if this rho is exactly pi star, then this quantity, the density ratio, is exactly 1. Okay, so let's say our data collection policy, it is a optimal policy, then this density ratio is 1, and the C single becomes 1. Okay? In this case, actually there are a long line of work from empirical work which motivates this problem, or motivates this assumption, and there's a theoretical work showing that this assumption is enough. Okay? You can show that with polynomial number of samples, you can learn a near optimal policy, and we also have some work on the gap dependence bonds. So, but here you do need to change the algorithm a bit. You need to utilize this pessimism. It's basically the counterpart of the optimism in the online setting. So the idea is, let's say in the bandit setting, you have some, say, 4 actions. You compute the mean, which are this orange line, and then you compute a confidence interval for each of the action. Then instead of choosing the highest mean action, you choose the action with the highest lower bound, which is action B. Okay, so you can generalize this idea to the MDP setting. Basically, you do some dynamic programming combined with this pessimism idea using some bonus bound, basically like UCB, but in the to the other direction. Then you can construct a pessimistic like bound, and then you can get the near optimal policy. So using this pessimism idea under this single policy coverage condition, you can show you can learn a near optimal policy. So that's what we know about single agent reinforcement learning in the offline setting. Okay. All right. So the main focus here is on multi-agent reinforcement learning. So Niall has taught a lot of the motivations. I won't repeat. So have games related to society decision making, cooperative robotics, and so on. So here we'll first consider arguably the simplest setting in multi-agent games. It's a 2-player zero-sum Markov games, and some applications especially in those games, competing games. So here the goal is to find a Nash equilibrium, and specifically for a 2-player zero-sum game, basically it's a pair of strategies that no player can do better by unilaterally changing the policy. Okay, so like a tic-tac-toe, then you play 1/3 probability for each of the action. All right, so so this is a formal setting for zero-sum Markov games. So you have 2 agents. Let's say it's SM state ST. Then these 2 agents choose a pair of action, AT and BT, and the state moves to the next state, ST plus 1, based on the transition probability, and you reveal some reward based on the current state and the action taken by these 2 agents, or T. Okay? So, and again, we repeat for each times. So we have 2 players. One is called max player, which tries to maximize the expected total reward. And we have a min player, which tries to minimize the expected total reward. Okay, so that's why they are competing agents. So this is a general tabular zero-sum Markov games. The main insights, actually, we can just look at the zero-sum bandits, which is much simpler, but illustrate basically all the insights in this multi-agent offline games. So this is like just a special case of Markov games. It's a two-player zero-sum Markov games, which h equals to 1. And let's say we only have one state, and basically only the reward matters. So at each round, you just choose a pair of actions and reuse the reward. One tries to maximize it, one tries to minimize it. Yeah? So PR, they are unknown. They are unknown. Okay. Yeah, they're unknown. But I mean, you have offline data. That's why you want to kind of learn them. Yeah. Any other questions? Okay. All right. So this is a formal metric to evaluate a pair of strategies. So let's say we learn a policy pair, mu and nu. The max player policy, mu, and the min player policy is nu. Generally speaking, this mu and nu, they are stochastic policies. Okay, so and then we can again define this Q function, say at some step h for the pair of searching mu and nu, starting from state S, taking action A and B, it just expected total reward. And you can also define the value function. So here, there's in multi-agent games, we need to define the best response for both max and min players. So given max player strategy mu, the best response for this mu is defined as the value of the value that you use the best min player to play against this max player mu. Okay, so basically try to find some nu such that it minimizes the value function. And we denote this as V mu star. And as a symmetry, we can also define the best response value for min player, given the min player policy or strategy nu. This V star nu is the maximum of the value function over the max player mu. Okay, so there exists a Nash equilibrium mu star nu star such that the value of the mu star nu star equals to the best response of mu star value, and also equals the best response value of the nu star. So this is some known classical results. So to measure how good a pair of strategy is, we look at the difference or kind of duality gap between the two best response values, V star nu and V mu star. Okay, so basically this is a best response gap from a max player and a min player. Okay, that's our metric. All right. So again, our goal is to find some mu and nu such that this gap is small enough. Okay, and again, we consider this two-player or tabular setting. We have finite state and actions, and sample complexity depends on polynomial on this factor. So here we have two set of actions, action A and action B for max and min players. Okay, and again, we consider the offline setting. So it's basically the same as single agent setting. We have data collection behavior policy pair. We call it rho, such that it generates our data set of this form. Okay, so it's the same form. The only difference is that the tuple now has state, action A, action B, and the reward. Okay, and we call this d rho H as a distribution that's induced by the data collection policy rho. Okay, so this is again our main question. Under what condition on d rho, our data collection policy and this induced distribution, we can learn epsilon closed Nash equilibrium. So the first question, which tries to basically we want to ask if we want to generalize the notion in the single policy coverage in the single agent reinforced learning to this two-player zero-sum game, does that condition enough for this two-player zero-sum game? Okay, So natural generalization will be something like this. So let's say we have a Nash equilibrium policy pair, mu star, nu star, and we have this our data collection policy pair rho. So this density ratio is upper bounded. So it's a natural generalization of the single agent setting. You just replace, basically replace the single agent distribution by the multi-agent, but only related to the optimal policy pair, mu star and nu star. Okay, so our first result basically shows that this is not enough, which gives you kind of a separation between single agent and multi-agent. Okay, and the example is super simple. So it's like this. So let's consider these two games. So this is max player and this min player, and let's consider two games, game 1 and game 2. So in game 1, so basically there are two actions here. It's action A, action A1, A2, B1, B2. So for max player, for choosing this pair and min player choosing this pair of action, it will get reward will be 0.5. And this pair will be 1, this pair will be 0, this pair will be 0.5. And for game 2, the only thing changes is that we switch the reward for this one and this one. Okay, so let's consider Nash equilibrium in these two games. So remember, the max player wants to maximize reward. So no matter what min player it will choose this action, okay, this row, okay, because I want to maximize reward. And the min player, it wants to minimize reward. So these are two actions. So the min player will also choose this row as action. So the Nash equilibrium will be this cell. Okay. Okay. So that's game 1, and for game 2, you can do the same calculations. Maxima wants to maximize the reward, so they will choose this row as an optimal action. And min player wants to minimize reward, so we will choose this row as the action. So the Nash equilibrium will be this cell. Okay. So Nash equilibrium for game 1 is A1, B1, and Nash equilibrium for game 2 is A2, B2. So now let's consider a data set, okay, which are generated by, let's say, playing this cell with half probability and this cell with half probability. Okay. Then we have D row A1, B1, D row A2, B2 equals to 0.5, and the C single is 2. Okay, so it's upper bounded. However, now consider what data you have. You have a data set, okay, which shows that you play A1, B1, you get reward 0.5. You play A2, B2, you have reward 0.5. And that's all you know. However, just looking at this data set, you cannot differentiate whether you are in the first game or the second game. Okay? Yeah. 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 Yeah, exactly. So this is considered a joint data collection policy. If it's a product policy, then basically you will cover all the cells. Then, of course, you can recover Nash equilibrium. No, I mean, if you have a product policy, like they are independent policy, then I mean, it's pretty straightforward to show you can recover the Nash equilibrium. It's like in a joint. Yeah, only in the joint case, if you have joint data collection policies, we can construct this counterexample. Oh, maybe I'm. Yeah, row is joint policy. Yeah, if it's a product, then I mean, essentially you can cover every cell. Then if you have data from every cell, then every state action pair or every state action tuples, then you have enough information to recover Nash equilibrium. Yeah. Yeah. So, but if there exist some cases that if your data collection policy is a joint policy and only cover like these cases, then it's not enough to recover the Nash equilibrium. Okay. Any other question about this example? Yeah. Yeah, but you use pessimism. So because you have, then you don't know, let's say you don't have any data from other arms, then you put a big penalty on other arms. So you would still choose the best arm. Let's say you only have data from the best arm, then your confidence interval for that arm will be very small, right? But for other arms, it's very big, and using pessimism, you would still choose the best arm. Yeah. Any other questions? Okay, so now we can consider under what conditions we can actually recover this Nash equilibrium, like going beyond the single policy coverage. Okay, so basically here, this example shows you do need some data from A1 or like this cell and this cell. Okay, so this is what we propose. Let's say a joint policy. We need this what we call unilateral coverage assumption. Basically saying for a Nash equilibrium mu star nu star, the behavior policy needs to cover mu star nu star and the mu star nu and the mu nu star for all deviation from unilateral deviation from this mu star nu star. Basically, we need to cover mu star nu and mu nu star for all mu and nu. Okay, so formally there exists some constant we call C unilateral, such that the density for d mu star nu over 0 and d mu nu star over 0 is upper bounded by some constant. Okay, and this constant is different from the single agent case. This constant is at least a plus b, which is number of actions. Okay, and there are some other cells, or kind of other. Can you imagine, like in other cells, these are not necessary to cover them, but you do need to cover. Let's say this is a Nash equilibrium. You need to cover this entire row and the entire column if this is the Nash equilibrium. This is conceptually what you can have in mind. Okay, and the algorithm is again based on the pessimism. So we, for every reward, let's say it's a bandit setting. For every reward, we construct some upper bound and the lower bound. Okay, and based on the lower bound, we compute a Nash equilibrium. Let's say mu subbar, nu subbar. And based on upper bound, we compute the upper bound's Nash equilibrium, mu upper bar, nu upper bar. And what we return is mu subbar and nu upper bar. So again, this is in the form of pessimism because we output the max players policy using the lower bound, and we output the min players policy using upper bound reward. So again, it's a generalization of the pessimism in a single agent setting. So this is for bandit. You can basically combine it with dynamic programming and some bonus to get the algorithm for like reinforcement learning or game setting as well. Okay, so in terms of bond, this is actually a tight bond. So we get like a suboptimal bond in 2022, and later there's a paper basically settles the sample complexity. It's a tight so it's a plus b h cubed c unilateral over epsilon squared. Okay, so basically, but the algorithm is the same. Basically, you use some tight bond for constructing the bonus, and then you do dynamic programming, and you use this pessimism, you can get a tight bond. Okay. So you can also consider whether we can consider a slightly weaker condition than this. Actually, we can show that it's not sufficient. So it's, in some sense, this condition cannot be weakened because even if we cover a slightly more cell, it doesn't help. So you do need this kind of unilateral coverage to recover Nash equilibrium. Okay. All right. So since I only have 5 minutes, you can also generalize this result to some general sum game setting as well. Still, it requires a unilateral coverage. It's also sufficient for Markov games, finding Nash equilibrium, and general sum game finding Nash equilibrium. And in this case, the unilateral can be, at least it's small, but it can also be exponentially large if you say you have a uniform coverage or uniform distribution over all action spaces. Okay, so in the last 5 minutes, I want to mention that if your game has certain structures, actually you require some kind of different coverage conditions, which gives this problem, kind of makes this problem a lot of more, have this richer structure if you have this additional assumption or condition in your games. So let's consider this congestion games. So what is congestion games? Basically, you have a network like of this form, and let's say you have 3 players. Each player is associated with like a source and a target. So for example, here you have T1, S1 to T1, which is basically a player wants to carry some goods from S1 to T1, and similarly from S2 to T2, S3 to T3. And you want to minimize the total cost of this transportation. Okay? So it's called congestion games. So formally, it has M players and say F facilities, which are these nodes here, and actions. So actions means that for each player, you choose a subset of the facility to transport your good from the source to the target. And the reward of this game is a sum of the each facility's reward. Okay, so it has this decomposition structure, and this reward only depends on how many players choose this facility to transport good. Okay, so that's called transport congestion game, which models like this traffic or this network-related problems. Okay, so here we can consider 2 kinds of feedback. One is called facility-level feedback. So if we can observe the reward from each individual facility, so this is practically relevant in the sense that in many cases, imagine you are playing, like cars are driving on the roads, and you know like how many cars on each road, and you know like the traffic condition from each road. So you do, in many real-world applications, you do get this facility-level feedback or reward. Of course, you can also get this agent-level feedback, which is the sum of basically, or this reward from each individual player. So if you only have agent-level feedback, you still need unilateral coverage. But if you have this facility-level feedback, actually you can use you can have a better or different coverage condition to enable learning the optimal policy for these congestion games. So what we call this facility unilateral coefficient, which is like this form. So basically, this is a form of formula. But basically, what it means that let's say you have 5 facilities. The optimal policy is that you have 2 players choosing facility 1, 3 players choosing facility 2, and so on. And what you need to cover in this case is that you only need this kind of 1 unit deviation from the optimal like allocation for these facilities. And I won't go into the details, but basically in this case, this constant can be as small as 0.1, which is much better than unilateral coverage, which also depends on the action space. Okay? So basically, this is just an example showing if you have more structure in your game, say more like this congestion game, and you have feedback is different, actually require a different coverage condition from the standard multi-agent games. Okay, so, and this is some sample complexity bound we got. All right, so here to summarize, so here for multi-agent games, or especially in the offline setting, the coverage assumption is really important. For a single agent game, we only need a single policy coverage. For 2-player zero-sum games, we need this unilateral coverage. For general sum games, again, you need unilateral coverage. And this, if you have game have certain structures, like congestion game, and you have the facility level feedback, then you need this kind of one-step deviation from the optimal policy kind of coverage. The algorithm is kind of just generalization of single agent games. You use this pessimism to construct confidence interval, and you use some standard reinforcement learning routines like value iteration or policy iterations. And that's it. I'm happy to take some questions. Yeah. Oh, you mean the algorithm idea? So yeah, again, it's like you put a kind of confidence interval around this reward. Basically, you construct confidence interval for each of the. So this reward only depends on how many players choose that facility, right? So you put for each facility and each case, which means that let's say basically for each cell here, which is each configuration, you put a confidence interval, and you choose a pessimism, use the pessimism idea applied for this confidence interval. So, okay, let's say you have 5 facilities, and you have this data set. Okay, so for each cell covered, or even not covered, but you can construct a confidence interval. Okay, and then you choose the according to the lower bound, you choose or like say, let's say you found the maximize reward, you choose the lower bound that can maximize the reward. That's your allocation. Reward. Yeah. There's some answer. Like say you have a noisy feedback, say given facility of say 3 people or 4 people choosing that facility. Yeah. 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 If they are independent, I don't think they can be beacon. It's pretty much, if they're independent, then essentially you need basically cover the entire action space, right? So I think so if in the independent policy, they need to cover yeah, so basically you need this data set to recover the Nash equilibrium, right? And if they are independent, then essentially you're also covering like this part. That's what I mean. Like, so essentially you're covering the entire action space. So in Bandit case, yeah, okay. For Markov games, I think you need something. Yeah, I think they should be the same, the entire action space, so that you can still cover the basic. Okay, so basically what you need is for each state, you need to have this unilateral coverage. So essentially, you still need to cover the entire action space. Yeah. I mean, if you have, I imagine if you have some special structure about the transition, then you might be able to weaken it a bit. Yeah. But yeah, there might be some way to weaken it if you have some structure on the transition. Any other questions? Cool. Thank you.